Hello, welcome to Learning Box. Today's discussing topic is K-nearest neighbors, shortly called as KNN. K-nearest neighbors is a straightforward and intuitive machine learning algorithm used for both classification and regression tasks. K-nearest neighbors KNN is a fundamental machine learning algorithm known for its simplicity and versatility. It is used in both classification and regression tasks, where it makes predictions based on the proximity of data points in a feature space. KNN is a lazy learning algorithm, meaning it doesn't explicitly learn a model from the training data. Instead, it retains all the data points and makes predictions by comparing the input to these stored examples. It is one of the simplest algorithms in machine learning and often serves as a baseline for more complex models. Understanding the KNN. The fundamental concept of KNN is that a point's classification or value is determined by the closest data points, the neighbors, to predict the label of a new point. For classification, the algorithm identifies the K-nearest neighbors and assigns the most common class among them. For regression, the algorithm calculates the average of the K-nearest neighbors' values. Important concepts in KNN. K-value. The number of neighbors considered K is a critical parameter. A lower K-value can lead to overfitting, while a higher K-value can result in underfitting. A common approach is to test various K-values to find the optimal one. Distance metric. This defines how distance is calculated between points. The Euclidean distance is common, but other metrics can be used depending on the data's structure. Normalization, standardization. Because KNN relies on distances, it is crucial to normalize or standardize features to ensure they're on the same scale. Lazy learning. KNN does not build a model during training. Instead, it retains all data and computes predictions on the fly, which makes it computationally expensive, especially with large datasets. Choosing the right value of K in K-nearest neighbors KNN is a crucial step in ensuring the algorithm's accuracy and robustness. The value of K determines how many nearest neighbors are considered when making predictions. Let's talk about how to select the optimal K value for your KNN algorithm. Impact of K on KNN. Low K. A smaller K value, for example, K equals 1 or K equals 3, can lead to overfitting because the prediction relies heavily on a small number of neighbors. This might make the model sensitive to noise or outliers. High K. A larger K value, for example, K equals 10 or K equals 20, tends to smooth out noise, leading to more generalized predictions. However, if K is too large, it can cause underfitting, resulting in a model that doesn't capture complex relationships in the data. Strategies for choosing the right K. Experimentation with different K values. Test a range of K values and evaluate the performance to find the optimal one. This approach involves plotting performance metrics, for example, accuracy, error rates against different K values. Cross-validation. Use techniques like k-fold cross-validation to assess model performance with different K values. Cross-validation divides the data into multiple subsets, ensuring that the model's evaluation is more robust and reliable. Elbow method. Plot the error rate against different K values to identify an elbow point, where the error rate stabilizes or starts to increase. This can be a good indicator of an optimal K. Grid search. For more automated approaches, use a grid search technique to find the best K value. This is common in machine learning pipelines with libraries like scikit-learn, allowing you to explore a range of K values and other hyperparameters. Contextual factors. Consider the size and structure of your dataset. Larger datasets may benefit from higher K values, while smaller datasets might work better with lower K values. Also, consider the data's dimensionality and distribution. Handling imbalanced data is crucial for machine learning models, including those using K-nearest neighbors KNN. Imbalanced data occurs when classes in a dataset are not equally represented, leading to biases in model predictions. Problems with imbalanced data are Bias toward majority class. Models tend to favor the majority class, resulting in high accuracy but poor sensitivity to the minority class. Reduced recall for minority class. This can lead to overlooking important instances, such as fraud or rare diseases. Skewed decision boundaries. Imbalanced data can distort decision boundaries, affecting model performance. Techniques for handling imbalanced data. Resampling techniques. Oversampling. Increase the number of samples in the minority class by duplicating existing data points or generating synthetic ones. Popular methods include the synthetic minority oversampling technique SMOT, which creates synthetic samples based on existing ones. Undersampling. Reduce the number of samples in the majority class to balance the data set. This can be risky if valuable information is lost. Algorithmic approaches. Adjust class weights. Some algorithms, including KNN, allow you to assign weights to classes, giving more importance to the minority class. Use different metrics instead of focusing solely on accuracy. Consider metrics that better capture performance on imbalanced data, such as precision, recall, F1 score, and the area under the ROC curve. Use cost-sensitive learning. Implement cost-sensitive classifiers where misclassifying the minority class incurs a higher penalty, encouraging the model to learn the minority class better. Ensemble methods. Balanced bagging. Use ensemble techniques that create balanced subsets of data during training, promoting diversity and reducing bias. Boosting techniques. Algorithms like AdaBoost and gradient boosting inherently focus on harder examples, which can help in cases of imbalance. Data augmentation. Synthetic data generation. Besides SMOT, other techniques can generate additional samples, such as variational autoencoders or generative adversarial networks. Augment features. Consider augmenting features to enhance model performance, especially if certain characteristics are underrepresented in the minority class. Evaluate with stratified sampling and cross-validation. Stratified sampling. Ensure that each fold in cross-validation maintains the same class distribution as the original dataset. Stratified train test splits. When splitting the data, ensure that both the training and testing sets have a balanced representation of classes. Feature scaling and normalization are key preprocessing steps in machine learning, especially when using algorithms like k-nearest neighbors KNN that rely on distance metrics. These techniques ensure that features contribute equally to distance calculations, leading to more reliable and accurate models. Here's a comprehensive guide on feature scaling and normalization, including when and how to use them. In distance-based algorithms like KNN, different scales among features can lead to inaccurate predictions. Feature scaling and normalization ensure that each feature contributes equally to the distance calculations. Since KNN relies on distance metrics, feature scaling or standardization is crucial to ensure all features contribute equally. Handling missing values in a k-nearest neighbors KNN algorithm requires careful consideration, as KNN relies on distance metrics that can be skewed by incomplete data. Here's a guide on how to handle missing values in KNN to maintain model accuracy and reliability. Challenges with missing values in KNN. Inaccurate distance calculations. Missing values can lead to incorrect distance calculations, affecting KNN's ability to find the nearest neighbors. Reduced accuracy. Missing data can cause inaccuracies in predictions and lower model performance. Potential for bias. Methods to handle missing values can introduce bias if not applied correctly. Strategies for handling missing values in KNN. Remove rows with missing values. Pros: simple and straightforward. Cons: can result in loss of valuable data, especially if a significant portion of the dataset contains missing values. When to use: if the dataset has a low proportion of missing values and the removed data does not significantly impact model performance. Impute missing values. Mean-median imputation. Replace missing values with the mean or median of the feature. This is simple but can introduce bias, especially if the data is skewed. Mode imputation. Replace missing values with the most frequent value. Useful for categorical data. KNN imputation. Impute missing values based on KNN, where the missing value is estimated by the average or mode of the k nearest neighbors. Pros: retains data and can be more accurate than dropping rows. Cons: imputation can introduce bias, and KNN-based imputation can be computationally intensive. When to use: if the dataset has a moderate proportion of missing values, and dropping rows would result in significant loss of information. Use specialized algorithms that handle missing values. Some algorithms can handle missing values without preprocessing, but KNN isn't typically one of them. Other techniques: for critical cases, consider using ensemble methods or advanced imputation techniques. Indicator variable for missingness. Add an indicator variable. Create a new binary variable indicating whether a value is missing. This can provide additional information to the model about missing data patterns. Pros: can improve model performance by accounting for the information contained in missing values. Cons: requires additional preprocessing and can complicate the feature space. When to use: if there are consistent patterns in the missing data, indicating they could be informative. Cross-validation is a crucial technique for evaluating the performance of machine learning models, including k-nearest neighbors KNN. It provides a robust method to test a model's ability to generalize to unseen data by partitioning the dataset into multiple subsets or folds. K-fold cross-validation is one of the cross-validation type. Benefits of cross-validation. Reduced overfitting. Cross-validation reduces the risk of overfitting by providing a broader assessment of the model's performance across different data splits. More reliable performance metrics. It yields a more stable estimate of a model's performance by using multiple testing sets. Comprehensive model evaluation. Cross-validation allows you to test a model against various segments of the dataset, leading to better insights into its strengths and weaknesses. Hyperparameter tuning is the process of optimizing the parameters that are not learned during training, but are essential for the performance of a machine learning model. In the context of k-nearest neighbors KNN, hyperparameter tuning involves selecting the optimal values for parameters like the number of neighbors k, the distance metric, and others that affect the model's behavior. Here's a guide on hyperparameter tuning for KNN and general practices to achieve optimal model performance. Key hyperparameters for KNN: number of neighbors k. Determines how many neighbors to consider when making predictions. A smaller k can lead to overfitting, while a larger k can result in underfitting. Distance metric. Defines how distances are calculated between points. Common metrics include Euclidean distance, Manhattan distance, and Minkowski distance. The choice of metric can significantly impact model performance, especially in high-dimensional spaces. Weighting of neighbors. Uniform weighting. All neighbors contribute equally to the prediction. Distance-weighted. Neighbors closer to the query point have a higher weight, providing a more localized prediction. Techniques for hyperparameter tuning. Grid search. Overview. Grid search involves defining a grid of hyperparameters and exhaustively trying all combinations to find the optimal set. Pros: simple to understand and can yield good results if the grid is well defined. Cons: computationally expensive, especially with many hyperparameters or large datasets. Example: testing different values of k, distance metrics, and weighting strategies. Random search. Overview. Instead of exhaustively searching all combinations, random search selects random samples from the hyperparameter grid. Pros: faster than grid search and can be more effective in exploring a large hyperparameter space. Cons: may not cover all possible combinations. Use cases: when computational resources are limited or when you have many hyperparameters to test. Bayesian optimization. Overview. Bayesian optimization uses probabilistic models to guide the search for optimal hyperparameters. It tries to find the best set of hyperparameters with fewer iterations. Pros: more efficient than grid search and random search, especially for complex hyperparameter spaces. Cons: requires more complex implementation and understanding of probabilistic models. Use cases: ideal for complex models and high-dimensional hyperparameter spaces. Common metrics for model evaluation: accuracy, the proportion of correct predictions among the total number of predictions. When to use: best for balanced datasets where all classes are equally represented. Precision, the proportion of true positives among all positive predictions. When to use: useful when the cost of false positives is high, for example, spam detection, medical diagnosis. Recall, the proportion of true positives among all actual positives. When to use: useful when the cost of false negatives is high, for example, fraud detection, safety critical systems. F1 score, the harmonic mean of precision and recall. When to use: provides a balance between precision and recall, useful for imbalanced datasets. Challenges and limitations of KNN. 1. High computational cost. KNN requires comparing the input data point to all points in the training set to find the nearest neighbors. This makes it computationally expensive, especially with large datasets or high-dimensional data. As the dataset grows, the computation time for predictions increases significantly, potentially becoming impractical for real-time applications. 2. Sensitivity to noise and outliers. KNN is susceptible to noise and outliers. A few anomalous data points can skew predictions, particularly when using smaller values of K. Outliers in the training set can significantly impact distance calculations and, consequently, model accuracy. 3. Choice of hyperparameters. Selecting the optimal number of neighbors K, distance metric, and weighting scheme requires careful tuning. An inappropriate choice of these parameters can lead to overfitting or underfitting. The right K value varies depending on the data, task, and other factors, requiring trial and error or grid search for optimization. 4. Distance metric limitations. KNN relies on a distance metric to measure the closeness of data points in high-dimensional spaces. Traditional metrics like Euclidean distance can become less meaningful due to the curse of dimensionality. The choice of distance metric can greatly influence performance, and selecting the wrong metric may lead to poor results. 5. Imbalanced data. KNN can struggle with imbalanced datasets, where one class has significantly more examples than others. This imbalance can lead to biased predictions and reduced accuracy for the minority class. Handling imbalanced data often requires additional techniques, such as resampling or adjusting class weights. 6. Lack of interpretability. KNN is often considered a black box algorithm, providing little insight into how it arrives at a particular prediction. This can be a limitation when model interpretability is crucial. Advantages of KNN are simplicity, flexibility, and no assumptions. Disadvantages of KNN are computational cost, sensitivity to noise, and choice of hyperparameters. Applications of KNN is used in a variety of fields due to its simplicity and versatility. Common applications include pattern recognition, recommendation systems, anomaly detection, and healthcare. In summary, KNN is a flexible and intuitive algorithm that can be a great starting point for machine learning tasks, despite its challenges. Proper tuning and pre-processing can lead to robust and reliable models. By understanding its limitations and applying the appropriate techniques, KNN can be used effectively across a range of applications. Thank you for watching. As always, if you haven't already, be sure to like, subscribe, and hit that notification bell so you don't miss any new videos. And feel free to share this channel with your friends. Let's keep growing our community. Enjoy machine learning.